So the purpose of this video is to take a look at regression modeling with splines. So let's follow Fairway here, and he creates this funky function. Okay, this is the function here called funky. It's funky because it behaves kind of strange, I guess. We can see that here in just a minute when we graph it. It must be funky because if Fairway says it's funky, then by golly, you know it's got to be funky. X will be a sequence from 0 to 1 by hundredths. That's 101 numbers in there from 0 to 1. Okay, and Y, let's set Y to be the value of this funky function plus some perturbation amount. Okay, some random perturbations generated by these standard normal random variables, pseudo-random numbers coming from this normal. We've got 101 of those, multiplying them each by a tenth and adding to the value of the function called funky. And we'll make a graph, we'll make a plot of all that stuff along with plotting that funky function. So this funky function here, this is the actual real life average response value. Ideally, this is what you want to know, but you'll never know it. In statistics, the idea is you never get to see this nice smooth curve. Instead, what you get handed to you after lots of work and money well spent, hopefully, is this random silly data point pattern. Okay, and your job is to infer the structure of this actual curve, right? That you don't actually get to see. Well, so let's make some polynomial models. I'll follow Fairway here. Follow Fairway far away. Haha. We'll make 4th degree and 12th degree polynomials using orthogonal polynomials there, just like he does in the book, and that's what this looks like. Okay, so here's the dashed line is my 4th degree polynomial model, and this other curvilinear model here is a 12th degree polynomial model. Wow, 12th degree. Yeah, you know what? Imagine if you made a 100th degree polynomial model, it would fit really, really well. In fact, you could fit just about as well as you want to if you keep on adding in higher degree terms. But of course, you know what happens there. You're basically modeling. You're overfitting your model. You're coming too close. Now you may look at this and think there are a few problems with this 12. There are some obvious problems with this 4th degree model, right? It just sort of doesn't map the trend of the data well enough. But the 12th degree polynomial model looks like it's also sort of inadequate in a sense. Its peaks aren't extreme enough, it seems like, and maybe this wiggle down in here is really a little too much overfitting or something. Okay, so one thing we can do is we can try to do it with try modeling with something called splines. Now, splines are similar to this broken stick regression or piecewise regression. The idea is that you model bits and pieces, certain segments of the data set, but in a smooth way, and you connect them. Okay. Now, spline modeling has an advantage over polynomial modeling in that, well, in the case of polynomial modeling, if I move a data point over here, it doesn't just affect the structure of the model or the evaluation of the model really over here locally. It affects it everywhere. You can see this in the case of simple linear regression. Recall that if you have a regression line running through this data point pattern, and if you move one of these points somewhere, it can have an effect. And in fact, it can have a very large effect. If you move it, say, far out to the right, it can have a large leveraging effect and be called an influential observation. Splines, that's not so much the case, really. Okay, you can move this point over here, and it'll affect what's going on over here locally, but not over here. So that's kind of nice. So to do this, we'll require the splines package, okay, and la-di-da. And splines require knots. You got to have some knots to tie these little ropes together, okay. So these are telling us, here we're just telling it where we want to put those knots, and we've got to have, turns out, 3 knots at the end points to make all this come out right. I'm going to let BX denote, like Fairway says, I'm just copying him. If you don't like something I do here, folks, it's Fairway's fault. BX is going to be spline design of knots, comma, X, whatever that is. Maybe I'll do a linear model then on this response, which is our response. Remember, are these up down these vertical direction y values. I'm going to try to model those versus bx, but without without a constant term in there. That's what this means. Oops, copied the wrong piece. There we go. Here's what I was talking about. Okay. And now I'm gonna get a new graph window, and I'm gonna partition that graph window into 2 columns, and copy what Fairway has in the book. Drop that in there. Now you can see what's going on here. So here's the end result. It looks a lot like our original funky function, right? It's sort of not so much overfit down here anymore. There's not so much of a wiggle. You can see it's got it's sort of kinky here. That's where the knots are. Okay, but it does seem to sort of, the extremes are a little bit more extreme. They come out to meet the points a little bit better. It certainly has a sort of a more fluid, gentle approach, or a more fluid, gentle sort of fit to our data point pattern. It's really pretty. These are our spline basis functions. This is how this stuff is constructed. Okay, it's basically a linear combination of these functions. Okay, these things are non-negative in certain regions and 0 in other regions. Okay, so that's why when you add these things together and combine them in a certain sort of best fit sense to our data point pattern, where these basis functions are 0, they're not going to have an effect in that region. Okay. Now I will leave you to reading about smoothing splines in the book. If you want to do smoothing splines, there you go. Okay. This gives you sort of a smoother approximation to the splining process. Okay.